Right now, the most precise instruments ever built are all returning the same answer. And the answer is that something is deeply, fundamentally wrong with our model of reality. The universe is expanding at two different speeds simultaneously. Dark matter has been searched for across 50 years and never found. Galaxies that shouldn't exist for billions of years are everywhere we look. The oldest light in the universe appears to know where Earth is. And across physics, chemistry, and biology, the knowledge we built our civilization on is quietly failing its own tests. If you stay until the end of this video, I promise you will not see the universe the same way again. Hit subscribe before we go further, because this is going to get uncomfortable. What you are about to hear is the story of how the instruments became precise enough to break everything we thought we knew. Ask yourself something right now, not tomorrow, not in the abstract, right now, sitting wherever you are, breathing air, feeling the weight of your own body pressing into that chair. Ask yourself, what if the universe you think you understand has been quietly wrong this entire time, and the only reason you never noticed is that your instruments weren't good enough to catch it? That is not a hypothetical. That is what happened. For most of human history, we built telescopes, pointed them at the sky, and got answers that confirmed what we already believed. The universe looked regular. It looked lawful. Every new instrument seemed to sharpen a picture that made sense. Galaxies moved, stars burned, planets orbited, the math worked. We felt, reasonably, like we were getting closer to the truth. Here is the part that should disturb you. We were not getting closer. We were getting more precise measurements of a universe we were fundamentally misreading. The instruments weren't good enough to show us how wrong we were, so we stayed comfortable. Think about what that means for your own life. Every assumption you carry, every fact you were taught in school, every confident explanation a scientist gave on television about what the cosmos is made of, how it began, what rules it follows. All of it was built on measurements that weren't sharp enough to reveal the cracks. The cracks were always there, we just couldn't resolve them. That changed around the second decade of this century, and it accelerated sharply after 2020. The James Webb Space Telescope launched. Detector sensitivity crossed new thresholds. Supercomputer simulations reached resolutions that exposed structures no model predicted. And for the first time in the history of science, multiple completely independent measurement tools, using completely different methods, pointed at the same sky and returned answers that flatly contradict each other. This is confirmed, peer-reviewed, replicated across instruments and research groups on separate continents. The golden age of precision and the golden age of contradiction arrived as the same moment. Scientists did not get better at confirming the model. They got better at breaking it. Every improvement in technology produced another anomaly. Every new data set widened an existing crack or opened a fresh one. The better we looked, the worse the picture became. Here is how this should land in your body, not your intellect. Right now, your atoms are obeying laws of physics we do not fully understand. The particles inside your cells are held together by forces our best equations describe incorrectly. The space between the molecules in your hand is threaded with a form of energy that makes up 68% of everything that exists, and we do not know what it is or whether it is even constant. We gave it a name, dark energy. Naming something is not the same as understanding it. Your body is not floating in empty space. It is sitting inside a universe that is currently embarrassing the people who study it for a living. You should know what they are finding. Most people don't. The data has been coming in since at least 2013, and it has been escalating every year. The scientists are not silent because nothing is wrong. They publish, they conference, they argue. They are silent in the way experts go quiet when a problem gets large enough that no one wants to be the person who says it plainly. So let's say it plainly. The universe does not behave the way our best theory says it should. And the gap between prediction and observation is not closing. It is widening. If the instruments were wrong before, and we didn't know it, what makes you certain they're right now? There is a number that should stop you cold: 5.0 sigma. If you've followed physics news at all, you've heard that number before. It is the threshold of certainty the scientific community requires before declaring something real. 5 sigma means the probability of the result being random chance is roughly 1 in 3.5 million. It is the standard that, when crossed in 2012, allowed physicists to say, the Higgs boson exists. That was considered one of the great confirmations in the history of science. Right now, 2 independent measurements of the same thing, the rate at which the universe is expanding, disagree with each other at 5.0 sigma. Same threshold, opposite implication. Instead of confirming a discovery, that number is announcing a contradiction so severe it has no resolution inside our current model of the universe. Here is what those 2 measurements are. The first uses the cosmic microwave background, the faint heat signal left over from the earliest moments of existence, 380,000 years after the beginning of time. Satellites mapped this signal across the entire sky in extraordinary detail. From it, physicists calculated a universe expanding at 67.36 kilometers per second for every megaparsec of space, which is roughly 3.26 million light-years. This is the early universe measurement. The second method measures the current universe directly. Astronomers use distance ladders, Cepheid variable stars, type Ia supernovae, galaxies whose brightness they know precisely. These measurements, led by the supernovae and Had-Zero for the equation of state team, return 73.04 kilometers per second per megaparsec. That is confirmed, independently verified, published in multiple journals. Those 2 numbers don't touch. They don't overlap within any margin of error. In January of 2025, cosmologist Daniel Skolnick of Duke University stood in front of the American Astronomical Society and made a declaration that should have interrupted every news cycle in the country. He said, "The Hubble tension is now a Hubble crisis." He meant that the level of disagreement has moved past the territory of measurement error, instrumental bias, or any known systematic problem. It is a genuine rupture in cosmology. John O'Meara, chief scientist at the Keck Observatory, put it plainly: cosmology as we know it may be broken. More than 500 researchers from around the world have now formed a consortium called Cosmoverse, dedicated entirely to this problem. 500 physicists mobilized around a single unresolved contradiction. That is not normal science. That is triage. Here is what this means sitting in the room with you right now. The atoms in your body, the floor beneath your feet, the electromagnetic signals your brain is using to process these words. All of it is embedded in a universe expanding at a rate we cannot agree on. The disagreement is not small. It is roughly 8%. In a universe that has been expanding for 13.8 billion years, 8% compounds into something catastrophic in terms of our models. Your entire existence rests on physical laws derived from a cosmological framework that is currently producing irreconcilable answers to its most basic question. How fast is space itself moving? We don't know. And the worst part is that we now know we don't know. Precisely. At 5.0 sigma certainty, both answers can't be right. What if neither one is? In 1917, Albert Einstein did something that should make you deeply uneasy about every confident equation you've ever trusted. He looked at his own general theory of relativity, arguably the most precise and tested theory in the history of physics, and decided it needed a fix. His equations kept producing a universe that moved, that expanded or contracted. He didn't want that. The universe, everyone believed at the time, was static and eternal. So Einstein added a term to his equations, a cosmological constant, a mathematical patch designed to hold the universe still. He made up a number and inserted it into the laws of nature. Then, in 1929, Edwin Hubble's observations confirmed that galaxies are moving away from each other. The universe was expanding. It had always been expanding. Einstein's patch was wrong, unnecessary, and embarrassing. He reportedly called it his greatest blunder. Now hold what happens next. In 1998, two teams of astronomers, one led by Saul Perlmutter and another led by Brian Schmidt and Adam Rees, observed that distant supernovae were fainter than expected. The universe wasn't just expanding, it was accelerating. Something was pushing it apart, faster and faster. They needed an explanation. Physicists reached back into Einstein's wastebasket and pulled out the cosmological constant. It fit. The math worked. Perlmutter, Schmidt, and Rees won the Nobel Prize in Physics in 2011. Einstein's greatest blunder was resurrected, rebranded as dark energy, and handed a Nobel Prize. Then the Dark Energy Spectroscopic Instrument collaboration, the Dark Energy Spectroscopic Instrument, began measuring the universe at a scale never attempted before. By March of 2025, they had released results from 14 million galaxy measurements, and the data returned something no one wanted to see. The cosmological constant may not be constant. It appears to be changing, weakening, evolving. The confidence level of this result sits at 4.2 sigma. This is the same mistake made twice. Einstein added the constant to stabilize a model. It was wrong. Physicists resurrected it to explain acceleration. That explanation now appears to be failing. The constant has been validated and invalidated not once, but twice across a century of physics. The thing you should feel is not shock that scientists were wrong. Scientists are wrong often, and that is how knowledge advances. What should make your stomach drop is the shape of this error. It is circular. The patch was wrong. We threw it out. We put it back. Now it's wrong again. At what point does the recurring failure of the same conceptual tool tell you something about the tool itself? Every structure of modern cosmology, the standard model of the universe, the lambda-cold dark matter model framework that describes everything from galaxy formation to the fate of time itself, is built partly on that constant. A constant Einstein invented to make the math comfortable. A constant that may be dissolving under 14 million data points as you read this. What other comfortable patches are still buried in our equations, holding the universe still so we don't have to look at what happens when they're removed? Take both numbers and hold them in your mind simultaneously. Early universe, 67.36. Late universe, 73.04. These are not measurements of two different things. They are two measurements of the exact same thing, how fast space itself is stretching, right now, in every direction, including through your chest. They disagree by roughly 8%, at 5 sigma certainty. With no overlap, there is a phrase physicists use when they want to be careful: tension. When two results are slightly off from each other, you call it tension. You assume there is a systematic error somewhere, a calibration issue, an unconsidered variable. You do not panic, you investigate. The Hubble tension was called tension for over a decade. Every investigation failed to close the gap. New instruments, new methods, new analysis teams. The gap stayed, then it widened. Then in December of 2025, the Keck Observatory published results from a technique called time delay cosmography, which measures how light from distant quasars bends and splits around massive galaxies sitting between the source and us. Each split image of the same quasar arrives at Earth at a slightly different time due to the geometry of the bend. That time delay is a clean geometry-based measurement of cosmic expansion. No Cepheid stars, no supernovae. Entirely independent of both previous methods, Keck returns 73 kilometers per second per megaparsec, matching the late universe measurement, confirming that the disagreement is real and not an artifact of any single technique. What this means, stated plainly, is that the universe appears to obey different rules at different stages of its life. The early universe, as read from the microwave background, produced a set of physical parameters. The current universe, as read by every direct measurement we attempt, produces a different set. These two sets of parameters are incompatible inside any existing model. You are not living in one coherent universe. You are living in what appears, from the data, to be a universe with a split identity. The universe of your atoms right now is expanding faster than the universe your atoms were part of when the first light traveled. Either something changed, and we have no mechanism for what changed or why, or our measurement of the early universe is contaminated by something we haven't accounted for, or the late universe measurements are being distorted by a structure we don't understand. Every option, every single one, requires either new physics or a fundamental error in old physics. Physicists like Wendy Friedman at the University of Chicago have argued for years that the distance ladder has rungs we haven't calibrated correctly. Possible, but 3 fully independent methods now return the same high value. The chance that all 3 are wrong in the same direction by the same amount, with unrelated systematic errors, begins to require more faith than the alternative. One alternative is that the universe changed its own rules somewhere between its birth and now. The space your body occupies is expanding at a rate that contradicts the rate the space around the universe's origin was expanding. What law of nature allowed that change to happen? And where else in the physics you depend on every second might that same unknown law be operating silently? 27%. Remember that number, because it describes something pressing against your body right now, threading through the walls of this room, passing through your skull at this exact moment, and we have never once, in 50 years of trying, directly detected even one particle of it. Dark matter, the invisible scaffolding that supposedly holds every galaxy together, including the one containing every star your eyes have ever seen. Without it, the math of galaxy rotation breaks completely. Galaxies should fly apart. They don't. Something is holding them. We called that something dark matter and assigned it 27% of everything that exists in the universe. Here is what we have actually found. Nothing. This is confirmed. The absence of detection is as confirmed as any positive result in physics. The LZ experiment, which stands for Lux Zeppelin, ran for 280 days inside a former gold mine in Lead, South Dakota, more than a mile underground. Its detector was shielded from cosmic rays by all that rock. It was filled with 10 tons of liquid xenon, cooled to precisely controlled temperatures. It was 5 times more sensitive than any dark matter detector ever built before it. Physicists from 35 institutions ran it around the clock looking for weakly interacting massive particles, the category of particle most theorists had been betting on for decades. Its detector found nothing. 280 days, 5 times the previous sensitivity. Not a single confirmed dark matter signal. Chamkar Garg of University College London, one of the lead researchers, described the situation like this. It is as if we have been told there is a magical fish in a lake. We believe it is there because the lake has effects we can't otherwise explain. We build a submarine. We search every corner of the lake. We still don't find the fish. What makes Gag's analogy particularly unsettling is what came after the LZ results. Physicists realized the detector had reached a new kind of wall. Background noise from neutrinos, the near massless particles generated by nuclear reactions inside our star and cosmic ray collisions in the atmosphere, had started to contaminate the signal range. This flaw is called the neutrino fog. It means there is a range of dark matter masses where it may be physically impossible to distinguish a dark matter signal from neutrino background noise, regardless of how sensitive your detector becomes. We have eliminated 75% of the predicted parameter space for weakly interacting massive particles. We have hit a wall we may not be able to see through, and the substance whose existence we are trying to confirm makes up more than a quarter of the entire universe. Right now, 27% of what exists is pressing through you with zero interaction, leaving zero trace, defeating every instrument we have. Or it doesn't exist at all. If dark matter is not there, then every simulation of galaxy formation, every map of cosmic large-scale structure, every model of how your galaxy and every other galaxy came to be is built on a fictional ingredient, which raises a question no one is comfortable answering. If the universe's dominant structural component is imaginary, what is actually holding everything together? Stop for a moment, pull back from the data, and ask a different kind of question. What does it mean to believe in something you have never seen, cannot touch, cannot detect with any instrument, and cannot test directly? What kind of knowledge is that? Dark matter has never been directly observed. Every piece of evidence for its existence is indirect. Galaxies spin in ways that require extra gravity. Light bends around galaxy clusters more than visible mass can explain. Large-scale cosmic structure in simulations only matches reality when dark matter is included. These are real observations. The reasoning from them to dark matter is careful and logical. But careful and logical is not the same as confirmed. This matters in a way that goes far beyond cosmology. Science has a long and uncomfortable history of confident, mathematically coherent frameworks that turned out to be wrong. In the 2nd century, Claudius Ptolemy built a model of the solar system with Earth at the center. It predicted planetary positions with impressive accuracy. When the predictions started drifting from observation, his followers didn't abandon the model. They added corrections, small orbital loops called epicycles, layered on top of epicycles, until the system became so complex it collapsed under its own adjustments. We now know the model was wrong at its foundation. Every epicycle was a patch on a broken premise. Look at what cosmologists are doing right now. Dark matter doesn't show up. Add a new form of dark matter with different properties. Adjust the interaction cross-section. Propose self-interacting dark matter, fuzzy dark matter, axion dark matter. The particle keeps changing shape to avoid detection. The model keeps absorbing the failure. This is speculation, not confirmed physics. But the parallel is direct, and the math of Ptolemaic adjustment is identical in structure to the math of dark matter rescue. There is a principle in the philosophy of science, named after Karl Popper, a theory that can absorb any result without ever being falsified is not a scientific theory at all. Dark matter, as currently practiced by some researchers, is approaching that boundary. Every null result produces a variant, and every variant remains safely beyond our detection threshold. Ask yourself what science actually is when it functions this way. Is it knowledge, or is it a system of increasingly elaborate explanations that preserve a model against the pressure of disconfirming data? The geocentrists were not stupid. They were brilliant, precise, committed to their craft. They were also staring at the wrong center. What if we are staring at the wrong center? The history of science is also the history of realizing the scaffolding was wrong. Ptolemy's followers never saw it coming. Einstein's contemporaries never expected his physics to shatter Newtonian certainty. Every generation of scientists is certain they have the basic framework right. What is the name of the thing we are certain about right now, in 2026, that will look like an epicycle to someone a century from now? For 40 years, the smartest people in theoretical physics worked on a single framework. They bet their careers on it. They published tens of thousands of papers, extending it, testing it, building structures on top of it. Graduate students were trained inside it. Careers were made defending it. It had a name, supersymmetry, or in physicist shorthand, SUSY. The theory was elegant in the way that good physics tends to be. Every particle in the standard model of particle physics, every quark, every electron, every neutrino, was proposed to have a supersymmetric partner particle, differing in a specific quantum property called spin. These partner particles would explain the hierarchy problem, the uncomfortable mathematical sensitivity of the Higgs boson's mass to quantum corrections. They would also, conveniently, produce exactly the kind of massive weakly interacting particle that dark matter theorists needed. Two of physics' biggest open questions. solved simultaneously by one framework. At CERN, the Large Hadron Collider was built partly to find them. It collides protons at energies that dwarf anything achievable before, energies sufficient to produce supersymmetric partners if they existed at the masses the theory predicted. The machine ran. The experiments ran. Hundreds of physicists analyzed the data. 0 supersymmetric particles were found. Not a hint. Not a statistical fluctuation that required explanation. Nothing. To understand how deep this cuts, consider what happened in 2015. A preliminary result from the Large Hadron Collider suggested a particle signal at an energy of 750 billion electron volts. More than 500 theoretical papers were written within months, proposing models to explain it. 500 papers. The community mobilized as if the signal were real. It had the shape, the location, the hint of something genuinely new. 2 years later, with more data, the signal disappeared. It was statistical noise. 500 papers, representing thousands of hours of work by some of the best theorists in the world, written to explain something that wasn't there. John Ellis, one of the most senior physicists at CERN, said in an interview he would be rather reluctant at this time to propose to a doctoral student a thesis based solely on supersymmetry. That is an extraordinary statement. Ellis has worked at CERN for decades. He helped build the theoretical frameworks that shaped modern particle physics. When a man like that says he would not send a young career down a particular path, he is saying something that the rest of the field has not yet admitted in public. Supersymmetry may be wrong. The most dominant theoretical framework in particle physics for 4 decades may describe a universe that does not exist. Your body is made of particles. Those particles obey laws described by the Standard Model. The Standard Model has problems, deep mathematical problems, that supersymmetry was supposed to solve. It didn't solve them, because there is no evidence it is real. The problems remain. They sit inside the equations that describe every atom in your hands right now, unresolved, patched with a framework that may be fictional. What happens to physics when the leading solution to its deepest problem turns out to be a 40-year detour? 68%. That is the fraction of everything that exists that is made of dark energy, the repulsive force driving the accelerating expansion of space. Take a moment to feel how large that is. You, your body, this building, the ground beneath it, every planet, every galaxy, every cloud of gas and dust you can observe in every direction, all of that accounts for roughly 5% of what exists. Dark matter is another 27%. Dark energy is 68%. You are living in a universe where 95% of everything is invisible to you, undetectable by any instrument you have, and understood only by its effects on the 5% you can actually see. And now the 68% appears to be changing. The standard assumption, embedded in the cosmological constant and every model derived from it, was that dark energy is a fixed property of empty space, constant, eternal. The same in every cubic inch of the universe, the same today as it was 10 billion years ago, the same as it will be 10 billion years from now. This was not proven. It was assumed because Einstein's framework required it, and because the early data didn't contradict it. At the heart of the effort to understand dark energy sits the Dark Energy Spectroscopic Instrument, a bank of 5,000 automated optical fibers mounted on a telescope at the Kitt Peak National Observatory in Arizona. Over several years, it has been mapping the 3-dimensional positions and distances of galaxies across a vast region of the observable universe. By March of 2025, the collaboration had analyzed 14 million galaxy measurements, making it the largest survey of cosmic structure ever conducted. The data suggests dark energy is not constant. It has been weakening, evolving. The best mathematical fit to the data returns a value called W0 of -0.838. The standard cosmological constant requires exactly -1.0. The gap is not enormous in absolute terms, but at 4.2 sigma, it is almost certainly not random. When the research team first unblinded the data in Hawaii in December of 2023, one physicist posted the graph to a messaging group with no accompanying text. Just an image of the data and an emoji of an exploding head. That is how physicists respond when they see something that breaks the model they've spent their careers building. Here is what changing dark energy means for your life right now. The expansion of space is threading through the room you're sitting in. The rate at which space is stretching through you, through the walls, through the air, is driven by dark energy. If dark energy is weakening, the future of the universe is different from what every textbook written in the last 25 years has told you. The universe was supposed to expand forever, driven by a constant force. If the force is not constant, the trajectory changes. Physicists do not yet know if the change is a slow decay, an oscillation, or the beginning of something that reverses. Each possibility changes the fate of every structure in the universe, including the one you are currently breathing inside of. The force that determines the ultimate fate of everything that exists may be dissolving, and no one has any idea why. If 68% of everything is changing in a way we didn't predict, what does that say about the 5% we thought we understood? Here is a number. Write it down if you want, though writing it won't make it any more comprehensible. 10 to the power of 123. That is the degree of discrepancy between what quantum field theory predicts the energy of empty space should be and what we actually measure it to be. Quantum field theory is the most precisely tested theory in all of science. Its predictions for things like the magnetic moment of the electron match experiments to within 1 part in 1 trillion. It is not a rough approximation. It is extraordinarily accurate about almost everything it touches. Then it calculates the energy density of the vacuum, the energy present in genuinely empty space, and returns a value of approximately 10 to the power of 76 giga-electron volts per cubic meter. This is not a rough estimate. It follows directly from the mathematics of quantum fields. We measure the actual energy density of the vacuum at 2.5 times 10 to the negative 47 giga-electron volts per cubic meter. The prediction is off from the measurement by a factor of 10 to the 123rd. Physicists call this the cosmological constant problem. They also call it, more bluntly, the worst theoretical prediction in the history of physics. This is confirmed. The calculation is correct. The measurement is correct. The gap between them is genuinely, catastrophically real. To feel the scale of this number, consider what Roger Penrose calculated about the fine-tuning of the universe's initial conditions. Penrose, one of the most rigorous mathematical physicists alive, computed the probability that the entropy of the early universe was arranged in the specific low-entropy configuration that allowed stars, galaxies, and life to form. His answer: 1 in 10 to the power of 10 to the power of 123. That is not 10 to the 123rd, that is 10 raised to the power of 10 raised to the power of 123. This number cannot be written out. If you used every atom in the observable universe as a zero, you would not have enough atoms to write the exponent. The number is larger than any quantity that has ever appeared in a physical equation, and it represents the precision with which the universe had to be set up at its beginning for you to exist right now. The energy prediction and Penrose's fine-tuning share the same number by mathematical coincidence, or by something that has no name in physics yet. Consider what this means for the space inside your body. The void between your atoms is threaded with vacuum energy. We cannot calculate correctly by a factor that defies human comprehension. Your existence depends on an initial precision we cannot explain, and the equation connecting those two facts is wrong by more than any equation has ever been wrong in the entire history of physics. If our best theory of reality fails by 10 to the 123rd, what would it even mean for it to fail more? You have now heard the number, 10 to the power of 123, the gap between what physics predicts and what physics observes in the same equation for the same quantity. Let it settle for a moment. Because the instinct most people have is to treat it as an abstraction, a large number that lives in a textbook somewhere and has no bearing on them. It has direct bearing on you. The vacuum energy threading through the space inside your atoms right now is set to a value that our best theory gets wrong by that factor. This is not a peripheral issue in cosmology. This is the central quantity in the equation that describes why the universe expands at all. The number is catastrophically wrong, and the expansion of space, happening through your body as you sit there, is the direct observable consequence of it. 3 explanations have been proposed for why the number works out to allow your existence. First, a divine designer set the constants precisely. The universe is fine-tuned because it was intentionally tuned. This explanation is coherent, internally consistent, and completely untestable by any scientific method. Second, there are an enormous number of universes, each with different values for its physical constants. In most of them, life cannot form. We exist in one of the rare universes whose constants permit observers. This is called the anthropic multiverse. It is coherent, mathematically motivated, and completely untestable by any scientific method. Third, our physics is fundamentally incomplete in a way we have not yet identified, and the actual mechanism that sets the cosmological constant is something we will eventually discover that explains why the number is what it is. This is also currently untestable, and every attempt to find such a mechanism, including supersymmetry, has failed. 3 explanations, none testable. Each one dissolves, when you push on it, into something that is not science, but philosophy. Not because philosophers are bad at their job, but because the question has reached a place where the usual tools of empirical investigation stop working. This should genuinely disturb you, not because religion and science are in conflict, not because philosophers have failed, because the most precisely described discrepancy in the history of physics has produced 3 candidate explanations and no way to choose between them using evidence. The horror is not the number itself. Every popular science video will tell you the number is large and then move on. The horror is what it means that every explanation we reach for evaporates into metaphysics the moment we try to test it. Science progresses by eliminating wrong answers. What happens to a field when the question it most needs to answer cannot, even in principle, be answered by the method that defines it? What happens to the humans living inside a universe whose most fundamental parameter is either divinely set, accidentally inhabitable, or based on a mistake no one has found yet? You are sitting in a room built from atoms governed by an equation that is wrong by a factor larger than any number ever written. And the people whose job it is to fix that equation cannot agree on whether the fix requires God, infinity, or a mistake no one has found yet. Which of those 3 keeps you up at night? And does it change your answer to know that no experiment you will ever live to see can tell you which one is correct? And yet, the fine-tuning of the cosmological constant is not the only place where the universe seems to have been threaded through a needle. Big Bang nucleosynthesis, the process by which the earliest light elements were forged in the first 3 minutes of cosmic time, is one of the most precisely tested theories in all of physics. It predicts, from the temperature and density of the early universe, exactly how much hydrogen, helium, deuterium, and lithium-7 the Big Bang should have produced. The predictions for hydrogen, helium, and deuterium match observations to extraordinary precision. They are among the great triumphs of the standard cosmological model. Then there is lithium-7. The predicted primordial abundance of lithium-7 is 4.924 times 10 to the negative 10 relative to hydrogen. Every old metal-poor star measured in the Milky Way's halo, the stars whose composition reflects the original primordial chemistry before later stellar processes could alter it, sits on what is called the Spite Plateau, described by Francois and Monique Spite in the 1980s. The observed abundance on that plateau is 1.6 times 10 to the negative 10. That is 3 to 4 times less lithium than the Big Bang should have made. The statistical significance of this discrepancy stands at 4.2 to 5.3 sigma. Above 5 sigma, in the words of the particle physics community, is a discovery. What makes this genuinely unnerving is its specificity. Deuterium matches, helium-4 matches, helium-3 approximately matches. Everything the Big Bang nucleosynthesis model predicts for the light elements confirms the model, except for this one specific element, lithium-7, which is off by a factor of 3 to 4. This is not a broad failure, it is a surgical one. Brian D. Fields at the University of Illinois wrote the definitive review of the problem in 2011 in the Annual Review of Nuclear and Particle Science. He framed it clearly: the predictions work everywhere except here, which almost makes it worse. A complete failure would suggest the model is broken everywhere. A failure in exactly one place, with everything else intact, suggests the model is mostly right and something very specific is wrong. And that specific wrongness has resisted every proposed solution for decades. A paper published in Astronomy and Astrophysics in 2025, catalogued as A and A701, a 164, claims a partial resolution through stellar population modeling, arguing that lithium in old stars may have been destroyed over billions of years. The claim is plausible. It is also contested. Even if stellar destruction accounts for some of the missing lithium, the magnitude of the depletion required is large enough to require its own explanation. The lithium problem has not been solved. It has been nudged, and a nudge at 5 sigma is still a crisis. The universe is telling us something very specific. It forged a precise amount of a specific element at a specific time, and that element is not where it should be. The remaining 2/3 are gone. Where did they go? We don't know. And the silence around that question, the absence of a satisfying resolution after decades of serious work, is a different kind of silence than the one in the LZ detector. The detector found nothing where something was predicted. Here, something was made and then vanished. The universe is not just failing to give us what we look for, it is hiding what it already produced. In 1912, a German meteorologist and geophysicist named Alfred Wegener published a theory. The continents, he proposed, had once been joined in a single supercontinent he called Pangaea, and had drifted apart over hundreds of millions of years. He had evidence. The shapes of the continents fit together like puzzle pieces. The rock formations on opposite sides of the Atlantic were identical. Fossils of the same animals appeared on continents separated by thousands of miles of ocean. The theory explained why the Appalachian Mountains in North America and the Scottish Highlands have the same geological signature. It explained the distribution of ancient glacial deposits. It explained dozens of things that the prevailing model, which assumed the continents were fixed, could not explain at all. The geological establishment rejected it comprehensively. Roland T. Chamberlain of the University of Chicago, in 1928, wrote, "If we are to believe Wegener's hypothesis, we must forget everything which has been learned in the last 70 years and start all over again." This was offered as a reason to reject the theory. The geological community called it Germanic pseudoscience. Delirious ravings, wandering pole plague, and moving crust disease. Students were explicitly told that interest in continental drift would ruin their careers. Wegener died in 1930 on the Greenland ice sheet, unvindicated. His theory was not accepted by the mainstream until the 1960s, when the mechanism of seafloor spreading was discovered and the physical evidence became overwhelming. Why did it take so long? Not because the evidence was weak. The evidence was strong from the beginning. It took so long because the people with power in the field had staked their careers and their authority on the fixed continent model. Accepting Wegener meant admitting they had been wrong, that their life's work was built on a false premise. The institutional structure of science, the tenure system, the grant system, the journal system, the way expertise is recognized and rewarded, all of it systematically protected the wrong answer. Max Planck observed this pattern from inside physics. A new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die, and a new generation grows up that is familiar with it. Science advances one funeral at a time. This is not ancient history. The same pattern has operated within living memory in multiple fields, and it operates today. The question it raises is direct. Right now, in 2026, which theories are being protected by the same mechanism? Which researchers have careers staked on models that the data is beginning to contradict? And which anomalies are sitting in the noise, unreported or underreported, because the people who found them know what happens to careers that challenge orthodoxy in ways the field isn't ready to accept. The Hubble tension is now a crisis. Dark matter is missing. Dark energy is changing. And yet the headline description of the universe, the one in textbooks, the one cited in funding applications, has not officially changed. The lambda cold dark matter model is still described as the standard model of cosmology. At what sigma level does a theory lose the modifier standard? What does it cost the people who would have to answer that question honestly? Take the oldest photograph in existence. Not a photograph of a person or a place, but a photograph of the entire universe, taken when the universe was 380,000 years old, before any star had formed, before any galaxy had condensed, before anything we would recognize existed. The cosmic microwave background is the thermal afterglow of the early universe, the radiation released when the first hydrogen atoms formed and the universe became transparent to light. Cosmology treats it as a near-perfect record of the initial conditions of everything. It is almost perfectly uniform. The temperature across the entire sky is 2.72 to 5 Kelvin, varying by only about 1 part in 100,000. Those tiny fluctuations, the quantum seeds that gravity would later amplify into the cosmic web of filaments and voids and galaxy clusters, are random. They should show no preferred direction. The universe, according to the cosmological principle, the bedrock assumption underlying all of modern cosmology, looks the same in every direction and from every point. No place, no direction is special, but the cosmic microwave background has something it should not have. The large-scale patterns in the temperature fluctuations, specifically the quadrupole and octopole modes, the longest wavelength variations in the map of the sky, are aligned with each other. That is already strange. Two independent patterns in the ancient light just happen to point the same way, like two different waves on a pond somehow choosing the same axis. But then you measure the direction they point, and they are aligned with the ecliptic plane of our solar system, the plane in which Earth orbits our star. The probability of this alignment occurring by chance is less than 0.3%, confirmed in the Planck satellite's final data release in 2023. Kate Land at Oxford and João Maguicho at Imperial College London named it the Axis of Evil in their 2005 paper. The name was a half joke and a serious statement simultaneously. The cosmological principle says no direction is special. The oldest light in the universe disagrees, and it specifically disagrees in favor of our local neighborhood of the cosmos. What are the options? Systematic measurement error, an artifact of how we remove the foreground emission from our own galaxy from the maps. This has been carefully studied and does not explain the alignment. A genuine statistical fluctuation, improbable, but possible in a universe as large as ours. This is the preferred explanation of most cosmologists, precisely because the alternative is worse. The alternative is that the universe has structure on scales larger than our current model allows, structure that imprints on the earliest light and creates the alignment we observe. Multiple independent observations, measurements of radio galaxies, galaxy clusters, quasars, and supernovae suggest the universe may actually be anisotropic, with a preferred axis. at 2 to 5 sigma significance. If the cosmological principle is violated, every calculation in modern cosmology that rests on it needs to be reconsidered. That is not one calculation. That is essentially all of them. The universe, in its oldest photograph, seems to know where you are, and the silence around that fact in mainstream cosmological discourse is, itself, worth noticing. If the universe knows where we are, or at least behaves as if it does, the next question is whether the universe is behaving the way we think everywhere else. The answer from the Flamingo simulation is no. Flamingo, run by a consortium of European cosmologists and published in December of 2025, is the largest and most detailed cosmological simulation ever completed. Roughly 300 billion particles, tracking the gravitational evolution of matter from the Big Bang to the present day. It included not just dark matter but ordinary baryonic matter, stars, black holes, and all of the feedback processes from stellar explosions and active galactic nuclei that redistribute matter in real galaxies. It was state-of-the-art. It was designed specifically to test whether the S8 tension, the discrepancy in how much matter has clustered into cosmic structures, could be explained by effects that simpler models had missed. The S8 parameter measures the combination of how much matter the universe contains and how clumped that matter is. The Planck satellite's measurement of the early universe predicts a value of roughly 0.8 to 3. Direct observations of the present universe using gravitational lensing, surveys like the Kilo Degree Survey, the Hypersuprime Cam Survey, and the Dark Energy Survey, consistently measure something closer to 0.7 to 5 to 0.7 to 8. The universe today is smoother than it should be. Matter has clustered less than the equations demand. Flamingo, with 300 billion particles and all the baryonic complexity previous simulations lacked, still predicted more clustering than we observe. The S8 tension was not resolved. The smoothness of the real universe cannot be explained by the physical processes the simulation included, and the simulation included everything we know how to model. The universe formed fewer and smaller cosmic structures than our best physics predict. Something slowed down the growth of those structures, or prevented them from forming, or redistributed matter in ways our model does not capture. The S8 tension is younger than the Hubble tension and carries a smaller sigma, but its significance is not in its size, it is in its character. The Flamingo result means the problem is not in the missing physics of small scales or the messy feedback of stellar processes. The problem is at a larger level. It is in the cosmological model itself, in the way matter in this universe responds to gravity across cosmic scales, or in the nature of whatever it is that counts as matter when you add everything up. This universe is not just expanding in two different ways simultaneously. It is also less organized than the laws governing organization predict. Every window we open onto the universe at higher precision shows us a universe that does not fit the box we have been building for it. And the boxes keep getting bigger and more sophisticated, and the misfit keeps getting clearer. What does it mean that the harder we look, the worse the match becomes? Let's pause. Right here, in the middle of this chain of anomalies, let's not add another fact yet. Let's instead ask you something directly. Every generation of physicists believed they were close to a complete theory. Newton's mechanics seemed to capture everything accessible to human measurement. Maxwell's equations unified electricity and magnetism and light into one framework, and the physicist William Thomson, Lord Kelvin, declared in 1800 that there was nothing important left to discover in physics, only more decimal places to calculate. Then came the photoelectric effect and the ultraviolet catastrophe and special relativity and the entire world of quantum mechanics, and the certainty of 1800 was exposed as a confidence built on ignorance of what it couldn't yet see. At the end of the 20th century, the same confidence returned. The standard model of particle physics plus general relativity covered everything from the smallest to the largest scales. The cosmological constant was back. Dark matter was predicted. The Higgs boson was expected. Physics was not finished, but the story was clear. The next Nobel Prizes would be awarded for filling in details, not rebuilding the architecture. Now consider your position. You're listening to a summary of what happened when the instruments got precise enough to test that confidence. The Hubble crisis. The cosmological constant problem unsolved after 40 years. Dark matter searched for 50 years and not found. Dark energy changing when it was supposed to be fixed. The James Webb Space Telescope galaxies that the timeline cannot accommodate. An axis of evil in the oldest photograph of the universe. A smooth cosmos that doesn't know how to clump. Here is the question. If you had been alive in 1800, listening to Lord Kelvin's confidence, would you have believed him? And if the answer is no, then what, right now, are you still believing without the instruments to know you're wrong? In 1982, a physician named Barry Marshall and a pathologist named Robin Warren, working in Perth, Australia, identified spiral-shaped bacteria in biopsies of inflamed stomach tissue. The bacteria were Helicobacter pylori. Warren had been seeing them for years. Marshall began systematically culturing them and testing whether they were associated with ulcers and gastritis. The association was overwhelming. The hypothesis, stomach ulcers, which afflicted hundreds of millions of people worldwide and caused enormous suffering, were caused by a bacterial infection. They were curable with antibiotics. The medical establishment did not receive this well. The prevailing theory, held for over a century, was that the stomach's highly acidic environment was sterile, that no bacterium could survive there, and that ulcers were caused by stress, lifestyle, and excess acid production. The pharmaceutical industry had built a multi-billion-dollar business on treatments for acid management, medications like cimetidine and ranitidine that reduced symptoms but never cured the underlying condition. Patients were on these medications for life. Curing ulcers with antibiotics was not a small proposition. It was a threat to an entire medical and economic ecosystem. Marshall could not get his paper published. He could not get a clinical trial approved. He attended conferences and found his presentations dismissed with the polite certainty that characterizes fields where the senior people are very confident in the wrong answer. In 1984, without ethics approval, he drank a culture of Helicobacter pylori. Within days, he developed gastritis, confirmed by endoscopy. He treated himself with antibiotics. The gastritis resolved. He had proven the hypothesis on his own body because the institutional pathways were closed to him. The establishment fought him for another decade. The Nobel Prize in Physiology or Medicine was awarded to Marshall and Warren in 2005, 23 years after their initial discovery. In the intervening years, millions of people with curable infections underwent unnecessary surgery, lived with chronic symptoms, took lifelong medications, and died of complications from a disease that could have been treated with a 2-week course of amoxicillin and clarithromycin. The cost of being wrong, when consensus is confident and the evidence is clear, is measured in human lives. What is the parallel today? Where is the evidence sitting in the open that the institutional structure of science is systematically ignoring because too many careers are built on the answer it contradicts? The Hubble tension has been 5 sigma for years. Dark matter has been undetected for 50. The cosmological constant has been wrong by 10 to the 120 for nearly 40 years. These are not new findings. They are old findings that have accumulated so much confirmatory evidence that they can no longer be called speculative, and the model they challenge is still called standard. What does that cost? In understanding, in misdirected research funds, in the questions that never get asked because the grant application would be denied before it was read? Here is the timeline. In 1996, the Hubble Space Telescope photographed a region of sky about 1/30th the diameter of the full moon, a region that had been observed to be essentially empty for almost 10 consecutive days. The resulting image, the Hubble Deep Field, showed approximately 3,000 galaxies in a patch of sky previously thought to contain nothing. Follow-up observations revealed that the observable universe contains roughly 2 trillion galaxies, each hosting hundreds of billions of stars. The James Webb Space Telescope, launched on Christmas Day of 2021 and fully operational from 2022, was designed to go further. Infrared sensitivity far exceeding the Hubble Space Telescope, a mirror 6.5 meters across. The ability to see galaxies at redshifts above 10, corresponding to the universe's first billion years. The timeline for how galaxies form begins with small, irregular, poorly formed structures in the early universe, gradually merging and evolving into the majestic spirals and ellipticals we see today. The James Webb Space Telescope was supposed to see the early stages of that process, the raw material before the architecture. Instead, it found finished buildings. In their 2023 paper, Ivo Labe at Swinburne University of Technology and colleagues reported massive galaxy candidates at redshifts above 7.4, corresponding to less than 800 million years after the Big Bang. The stellar masses of these candidates were up to 10 to the 11th solar masses, as massive as the most massive galaxies in the present universe. They were not supposed to be there. The standard model allows for some large galaxies to form early through rare density fluctuations, but not in these numbers and not at this mass. Michael Boylan Colchin at the University of Texas at Austin published a stress analysis showing that the density of these massive early galaxies exceeded what the lambda cold dark matter model could plausibly accommodate. The James Webb Space Telescope found galaxies more than 10 times more common than predicted at high redshifts. It found them forming stars at rates that, per unit of available gas, essentially required every atom in the vicinity to become a star immediately. It found the most distant confirmed galaxy in 2025 at a redshift of 14.424, placing it at an age of approximately 290 million years. The universe at that age is supposed to be a sparse, cool fog of hydrogen and helium with only the very first generation of stars beginning to flicker on. Instead, the James Webb Space Telescope found a galaxy. Subsequent analysis by Chwarovsky and colleagues in 2024 refined the statistics and showed that after accounting for contamination and recalibration, the anomaly is real, but its magnitude is debated. The galaxies don't literally break the lambda cold dark matter model in a way that would require abandoning it entirely. They stress it. They push at its edges in ways that require either revision of the processes that govern early galaxy formation or revision of the cosmological model itself, or both. Erica Nelson at the University of Colorado Boulder, working on a related James Webb Space Telescope survey, captured the scientific community's response with a precision that no technical language achieved. It's bananas. The universe apparently spent its first few 100 million years building what should have taken billions of years to construct. And we're standing in those buildings now, using telescopes powerful enough to see them, feeling for the first time the specific texture of how wrong our timeline was. Those impossible galaxies are alarming. But they are at least galaxies, objects with a category, a name, a place in our taxonomy. The James Webb Space Telescope found something else in the early universe that doesn't fit any existing category at all. They are being called little red dots, a name that conveys both their appearance in infrared imaging and the inadequacy of our vocabulary for them. They are compact, very red, and found across a wide range of cosmic distances, particularly abundant in the first few billion years of the universe. Initial analysis suggested they were a previously unrecognized population of active galactic nuclei, galaxies with very actively feeding central black holes. But the number of them, their compactness, and their spectral properties have resisted clean categorization within the framework of known black hole and galaxy physics. A paper published in Astronomy and Astrophysics in September of 2025 proposed that they might be black hole stars, a class of object theorized but never before observed. Giant spheres of gas, so massive and dense that instead of being powered by nuclear fusion, the way ordinary stars are, they are powered by the gravitational energy of a supermassive black hole at their center. If black hole stars exist, and the little red dots are them, then the taxonomy of cosmic objects we have used for the last century is missing an entire category. Stars, galaxies, black holes, nebulae, these are the objects we have built the vocabulary of astrophysics around. Black hole stars would be none of these, and all of these simultaneously, a new kind of thing that the universe was apparently making in enormous numbers during its earliest epoch. In November of 2025, Roberta Tripodi at the University of Ljubljana published observations of a galaxy designated Canucks LRD Z8.6 at a redshift of 8.6, corresponding to 570 million years after the Big Bang, hosting a supermassive black hole growing far faster than any model predicts should be possible at that age. The architecture of the early universe is not what we thought. We thought we understood the sequence. Small galaxies forming first, merging slowly over billions of years into large ones. Black holes growing gradually at their centers, the whole process unfolding over cosmological time. The James Webb Space Telescope is showing us a different sequence, one that is either much faster or much more efficient or simply doesn't follow the rules we wrote for it. The universe is not explaining itself. It is presenting the evidence and leaving us to figure out what framework could possibly accommodate it. And right now, we do not have one. Every few seconds, somewhere in the observable universe, there is a flash. It lasts for a millisecond. During that millisecond, it outshines every star in an entire galaxy combined. It releases more energy than our star emits over an entire year, and it does this in the time it takes you to blink. Then it is gone. No repeat, no follow-up emission at other wavelengths. Just a pulse of radio waves so brief and so energetic that the instruments that detect it take longer to record the event than the event itself takes to happen. Fast radio bursts were discovered in 2027 by D.R. Lorimer at West Virginia University, analyzing archival data from the Parkes Telescope in Australia. Since then, the Canadian Hydrogen Intensity Mapping Experiment Telescope in British Columbia has detected thousands of them, localizing over 100 to specific host galaxies. The source distances range from relatively nearby to 5 billion light-years. The energetics are extreme. The duration is extreme. The brevity suggests an emitting region no larger than a few hundred kilometers across, which means whatever produces a fast radio burst is compact, a neutron star, most likely, or something comparably dense. In 2025, Kenzie Nimmo at the MIT Kavli Institute and colleagues published an analysis of a fast radio burst designated Fast Radio Burst 20221022A. Using the timing and morphology of the burst, they traced its emission to within 10,000 kilometers of a neutron star magnetosphere. 10,000 kilometers. This is extraordinary precision, comparable to pointing at a specific tree from across the continent. The confirmation, at least some fast radio bursts, come from magnetars, neutron stars with magnetic fields so intense that they periodically fracture the star's crust, releasing catastrophic bursts of energy. Case established, the mystery partially closed. Then came Fast Radio Burst 202402009A, detected in February of 2024, localized in January of 2025 by Taraneh Eftekhari at Northwestern University and Calvin Leung at the University of California, Berkeley, using the Canadian Hydrogen Intensity Mapping Experiment Outrigger Network. The host galaxy, a massive, dead elliptical galaxy, 11.3 billion years old, an old galaxy, a dead galaxy, a galaxy that stopped forming stars long ago and has had no young stars for billions of years. Magnetars are formed in the supernova explosions of massive young stars. They live, by astronomical standards, briefly. They require young stars to exist, the fast radio burst. 20240209, a host galaxy has no young stars. It has not had young stars for billions of years. One fast radio burst, confirmed from a neutron star magnetosphere. Another confirmed from a galaxy where no magnetar should exist. Same phenomenon. Mutually exclusive origins. Both confirmed, both real, both measured. Tarane Eftekari. This new fast radio burst shows us that just when you think you understand an astrophysical phenomenon, the universe turns around and surprises you. Two confirmed, mutually exclusive explanations for the same phenomenon. Let's stay here for a moment, because this is a different category of problem than anything we've discussed so far. The Hubble tension is a contradiction between two measurements. The cosmological constant problem is a contradiction between two theories. The dark matter, non-detection, is an absence. But fast radio bursts are a confirmed contradiction at the observational level. We know fast radio burst 20221022 A came from a magnetar. We know fast radio burst 20240209 A came from a place where no magnetar can exist. These are not competing theories. They are both empirically established facts, and they cannot both be facts about the same type of object without requiring that the category same type of object be wrong. Either fast radio bursts are not a single phenomenon with a single origin, in which case our entire framework for categorizing astrophysical transients needs revision, or the universe has found a way to produce these events through at least two fundamentally different mechanisms that happen to produce nearly identical observational signatures, in which case the physics of compact objects is far richer and stranger than anything in our current models. There is a third possibility, the one that is hardest to articulate without sounding dramatic, but which is what the data forces you toward if you take it seriously. The universe may operate by rules that don't resolve into the kind of tidy causal chains our physics demands. When we observe a fast radio burst, we assume there is a single process that produced it, a mechanism that, in principle, we could fully describe. But what if some phenomena resists that description? What if the universe contains events that are observationally identical, but mechanistically incommensurable? You are sitting here being asked to absorb the idea that the same flash in the sky can simultaneously confirm and refute the best theory we have for what produces it. That is not a statement about uncertainty. That is a statement about the structure of the world. And what it forces you to ask is, how many other things that we think we understand are built on a foundation that contains an unnoticed contradiction at the observational level, waiting for the instrument precise enough to show it to us? There is a theory that has been tested more rigorously than any other in the history of human inquiry. It predicts the magnetic moment of the electron to 11 decimal places, and the prediction matches the measurement to that precision, a feat of agreement so extraordinary it has been compared to predicting the distance from New York to Los Angeles to within the width of a human hair. This theory has given us transistors, lasers, the entire semiconductor industry, the mechanism by which your retinas absorb light. Quantum mechanics works, and after 100 years of it working, there is still no agreed answer to the question of what it means. This is not a minor philosophical footnote. The interpretation of quantum mechanics is not a question about language or framing. It is a question about the structure of reality itself. When a quantum particle is unobserved, it exists in a superposition of possible states. When you measure it, you get one outcome. The question is, what happened between the unobserved superposition and the measured result? The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, says the wave function collapses upon measurement, but offers no mechanism for how or why this happened. Many worlds, proposed by Hugh Everett in 1957, says the wave function never collapses, that every possible outcome actually occurs in a branching tree of diverging realities. Pilot wave theory, developed by Louis de Broglie and David Bohm, says particles have definite positions at all times, guided by a hidden wave that we never directly observe. These three interpretations are mutually exclusive. They make different predictions about the structure of reality at the deepest level. And after 100 years, physicists have not agreed on which one is correct, or whether any of them is correct. John Wheeler went further. Wheeler, the physicist who coined the term black hole and spent his career probing the boundary between quantum mechanics and general relativity, proposed what he called the participatory universe. The act of observation, Wheeler argued, does not merely reveal a pre-existing reality, it participates in creating it. The universe, in his framework, is not a collection of objects with fixed properties that exist independently of being measured. It is a network of participatory acts, and those acts reach backward and forward in time. His delayed choice experiment, which has since been performed and confirmed in multiple laboratories, shows that a quantum decision made after a photon has already passed through a beam splitter can retroactively determine which path that photon took. The measurement you make now appears to influence events that already happened. If Wheeler's participatory universe is correct, then the universe existed in an indeterminate state for billions of years before anything arose to observe it. It sat in superposition across cosmic time, across its own early history, without a defined structure, until the emergence of something that could measure it. And if that is true, then you, sitting here right now, your act of conscious observation, is part of what constituted the universe's history, not metaphorically, literally, which raises a question that should make the room feel slightly different. Who collapsed the wave function before there was anyone here to collapse it? There is a problem at the edge of a black hole that two of the most successful theories in the history of physics have been fighting over for 50 years, and neither theory has won. General relativity. Einstein's description of gravity as the curvature of space-time predicts that information can fall into a black hole and disappear permanently as the black hole slowly evaporates. This is not unusual under general relativity. Information can get scrambled, objects can be destroyed, causality flows in one direction. Quantum mechanics says this is impossible. Unitarity, the principle that the total probability of all quantum outcomes always sums to 1, is not a preference or a guideline. It is a hard constraint on how the universe evolves. Information cannot be destroyed. Every process, at the quantum level, is, in principle, reversible. If you knew the state of every particle in a burning book with complete precision, quantum mechanics says you could reconstruct the original text from the ashes and smoke. The information is not gone. It is encoded differently. But a black hole evaporating via Hawking radiation, the thermal radiation that Stephen Hawking predicted in 1974, appears to carry no information about what fell in. It is random thermal noise. The information appears to be erased. Stephen Hawking spent decades defending the position that black holes genuinely destroy information, that quantum mechanics would have to be modified. Leonard Susskind spent the same decades arguing that information must be preserved, that general relativity must be the thing that gives. In 2013, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully published what became known as the firewall paper. They showed that if information escapes a black hole, then an observer falling into that black hole must encounter an enormous wall of energy at the event horizon, a firewall, and be incinerated before crossing it. This violates general relativity's equivalence principle, which says that crossing an event horizon should be locally unremarkable for a free-falling observer. Nothing special should happen there. So the choice is this: either information is destroyed, which violates quantum mechanics, or information is preserved, which means a falling observer is incinerated at the horizon, which violates general relativity. Both theories have been confirmed to extraordinary precision in their respective domains. Both make a clear prediction in this scenario. Those predictions are mutually exclusive. The universe cannot satisfy both simultaneously. And yet the universe is not asking for our permission to exist. The black holes are there. The information paradox is real, and the two best theories we have cannot agree on what happens inside the most extreme objects in nature. The best current attempt to resolve the information paradox involves a concept called entanglement islands. The proposal, developed by Ahmed Almheri and colleagues in a series of papers from 2019 to 2021, involves a region of space-time just inside the event horizon of a black hole, a region approximately 1 Planck length wide, roughly 10 to the negative 35 meters, close to 1 atomic diameter, through which quantum information can be transmitted to the exterior via entanglement. The entangled particles just outside the black hole share a quantum connection with these island regions just inside it, and through this connection, the information that fell in can, in principle, be reconstructed by someone outside. This is currently the leading candidate for a resolution to the information paradox. It is supported by calculations in the anti-de Sitter space and conformal field theory correspondence, a framework developed by Juan Maldacena in 1997 that has become one of the most studied ideas in theoretical physics. The correspondence maps certain quantum gravity theories to theories without gravity in a way that allows calculations that would otherwise be impossible. It is powerful, elegant, and technically extraordinary. It also requires that space-time is fundamentally non-local. Non-local means that two regions of space, separated by vast distances, can be directly connected in ways that don't pass through the space between them. The Entanglement Islands proposal suggests that the interior of a black hole and the exterior radiation field are connected through a quantum channel that bypasses the geometric structure of space-time. Space, in this picture, is not the fundamental fabric of reality, but an emergent property of something more primitive, the network of quantum entanglement between degrees of freedom that don't individually live anywhere in particular. If space-time is emergent, then asking where something is located is like asking which ocean wave a particular water molecule belongs to. The question has an answer, but the answer is downstream of a deeper reality that doesn't care about waves. The Entanglement Islands proposal solves one problem. It leaves you with another. The structure of reality at its most fundamental level is not space and time with things in them. It is something else that we do not have a complete theory of, from which space and time emerge. The resolution to the black hole information paradox points toward a universe more abstract and more alien than anything we have built institutions to study. What specific version of that universe are we currently sitting inside? All of cosmology rests on a single axiom so foundational that most textbooks never state it explicitly. The cosmological principle: the universe is homogeneous, meaning the same everywhere, and isotropic, meaning the same in all directions, when viewed at large enough scales. This principle is not a theorem. It was never derived from deeper physics. It was adopted in the 1920s because it made Einstein's equations tractable. With the cosmological principle, the field equations of general relativity simplify from an impossible tangle into the Friedmann equations, which can be solved by hand. Without it, modern cosmology as it has been practiced for a century is not possible. The cosmological principle has never been directly confirmed. It has been assumed. The expectation was that as surveys became larger and more precise, the universe would reveal itself to be uniform at the expected scales, and the principle would be vindicated empirically. Instead, the surveys have found structure. The Sloan Great Wall, discovered in 2003, is a filament of galaxies 370 megaparsecs long, larger than models predicted. The Hercules Corona Borealis Great Wall, identified in 2023, extends over 10 billion light-years, a scale at which the cosmological principle demands the universe be smooth. The structure observed in quasar distributions, analyzed by Subir Sarkar and colleagues at Oxford, showed statistical anisotropy at over 5 sigma in a 2017 paper. Though this remains contested, the axis of evil in the cosmic microwave background aligns with the ecliptic plane of our solar system at a probability of less than 3 in 1,000. Each of these results, taken individually, can be explained away or disputed. Taken together, they form a pattern. The universe is less uniform than the cosmological principle requires, and the deviations are appearing in multiple independent datasets, measured at multiple scales, using multiple techniques. In a 2023 review in the journal Nature Astronomy, Subir Sarkar and his group catalogued the evidence and put the challenge plainly. If the cosmological principle is violated, then the standard cosmological model is built on a false foundation, and every equation that begins with that assumption produces a result that is systematically biased. Every equation in standard cosmology begins with that assumption. Every calculation of the Hubble constant, every prediction of structure formation, every constraint on dark energy. The standard model is not a set of isolated results. It is an interconnected edifice, and the cosmological principle is the ground it stands on. If the ground is uneven, the entire structure tilts. You are sitting inside a universe that may be fundamentally asymmetric, that may have a preferred direction written into its oldest light and largest structures. And every model you have ever heard described as the definitive account of cosmic history was calculated by first assuming that isn't true. Let's stop the cascade of physical anomalies for a moment and point it somewhere you didn't expect. At you. At the specific experience you are having right now of listening to these words, of following a thread of reasoning, of feeling something like unease accumulating as the list of contradictions grows. You are having a subjective experience. This is the least controversial fact about your existence. You know, with more certainty than you know anything physics has told you, that there is something it is like to be you, right now, in this moment. Neuroscience cannot explain that fact. Not at the edges, not in the fine print. At the center, after more than 100 years of modern neuroscience, including the complete mapping of the wiring diagram of entire organisms and the detailed measurement of neural activity in every part of the human brain during every kind of experience, no mechanism has been identified that explains why physical processes in neurons give rise to subjective experience at all. We can correlate neural activity with reported experience. We can identify which brain regions are active when you see red or hear music or feel pain. We cannot explain why those correlations exist, why there is an inside to the experience rather than just physical processing happening in the dark. The philosopher David Chalmers called this the hard problem of consciousness in 1995. And the name has stuck because the problem has resisted every attempted solution. The easy problems of consciousness, explaining how the brain processes sensory information, integrates it, produces behavior, these are difficult technical problems, but they are in principle explicable within the current framework of physical science. The hard problem is different. Why does any of this processing feel like anything? Why isn't it all happening in the dark, producing behavior without experience? You could, in principle, imagine a physical system that processes information exactly as your brain does, but has no inner life, no felt quality to any of it. Why are you not that system? Some physicists and philosophers, including Roger Penrose and Stuart Hameroff, have proposed that consciousness involves quantum processes in structures called microtubules inside neurons, bringing the measurement problem of quantum mechanics directly into the problem of consciousness. Others have argued for integrated information theory, panpsychism, or other frameworks that attribute some primitive form of experience to all matter. None of these proposals commands consensus. None of them has made a precise, testable prediction that was subsequently confirmed. The hard problem remains unsolved because the framework of physics, as currently understood, may not contain the right concepts to solve it. The disturbing implication is this. Physics is the project of describing the universe from the outside. Consciousness is the fact that there is no outside, that everything we know about physics is known from inside an experience. The observer has no place in the theory of observation. And since observations are how we test physics, there is something circular and incomplete at the foundation of the whole enterprise. The universe, in this light, is not just failing to make sense at the cosmological scale. It is failing to make sense at the scale of the person trying to understand it. In 2015, the Dark Energy Spectroscopic Instrument collaboration, the Dark Energy Spectroscopic Instrument team at the Kitt Peak National Observatory in Arizona, was building the spectrograph that would eventually measure 14 million galaxies and produce the most precise constraints on dark energy in history. That same year, a separate collaboration published a paper that received enormous attention and almost none of the right kind of scrutiny. The paper reported that a major replication project had attempted to reproduce 97 significant results in psychology. The replication rate, 36%, 64% of landmark findings in psychology, results that had been cited thousands of times, incorporated into clinical practice, used to design educational interventions and corporate management strategies, and public health campaigns, could not be reproduced. The studies that failed to replicate included some of the most influential findings in the social sciences. Ego depletion, the theory that willpower is a finite resource that can be exhausted, which had generated over 500 follow-up papers. Priming effects, the idea that exposure to certain words or images can unconsciously influence subsequent behavior. The facial feedback hypothesis, the claim that the physical act of smiling makes you feel happier. Each of these results had shaped real decisions, affecting real people. Each failed to reproduce under rigorous conditions. Replication failures are not limited to psychology. In cancer biology, a 2012 effort to replicate 53 landmark preclinical studies, results that had been used to justify clinical trials and pharmaceutical development, found that only 6 of the 53 could be reproduced, 11%. Biostatistician John Ioannidis published a paper in 2025 in the journal PLOS Medicine titled "Why Most Published Research Findings Are False," and the arguments in it have not been convincingly refuted in the 20 years since. The problem is structural. Publication bias favors positive results. Statistical thresholds are often applied selectively. Researchers make dozens of analytical choices during data processing and analysis, and those choices can collectively produce significance from noise. Everything you have absorbed over your lifetime, the facts you accept about human behavior, about psychology, about medicine, about nutrition, is not a clean collection of confirmed findings. It is a mixture of real results, artifacts of measurement, and false positives that became canonical through citation velocity rather than replication. Some percentage of what you believe is simply untrue. You do not know which percentage or which beliefs. The anomalies in physics are frightening because they challenge our model of the cosmos. The replication crisis is frightening because it challenges our method of knowing anything at all. Now, consider how these two threads come together. The universe is behaving differently than our model predicts. Our method for building and testing models is producing results that don't hold up. Both the content of scientific knowledge and the process by which it is generated are showing structural cracks simultaneously. And the most important question this raises is not philosophical, it is practical and urgent. Where is the correct theory? Max Planck's observation that science advances one funeral at a time was not a cynical remark. It was a careful empirical observation made by a man who had watched his own field resist the quantum revolution he helped create. The physicists who defended classical mechanics at the turn of the 20th century were not stupid. They were the most brilliant physicists alive. They were defending a framework that had worked for 2 centuries, that had produced enormous predictive successes, and that they had staked their careers, their reputations, and their sense of intellectual identity on. Accepting quantum mechanics meant accepting that everything they had done was built on an incomplete foundation. The personal cost was real. Today, researchers working on modified gravity theories, like modified Newtonian dynamics, have produced a framework that correctly predicts the rotation curves of dozens of galaxies without invoking dark matter, using a single additional parameter. The theory is not popular at major cosmological institutions. Its primary architect, Mordechai Milgrom of the Weizmann Institute of Science, has never won the Nobel Prize despite the empirical success of his predictions. Erik Verlinde at the University of Amsterdam has proposed emergent gravity, a framework that derives gravity from entropy rather than treating it as a fundamental force, and which reproduces certain observed features of galaxy clustering without dark matter. These ideas are not fringe. They are peer-reviewed, empirically motivated, and increasingly cited as dark matter non-detection has accumulated. The standard model protects itself through the same mechanisms that protected fixed continents, the ether, the sterile stomach, and classical mechanics. Grants go to projects that use standard frameworks. Journal reviewers are trained in standard frameworks. Hiring committees select for expertise in standard frameworks. A graduate student proposing a dissertation on emergent gravity faces the same career landscape Barry Marshall faced in gastroenterology in 1984. The correct answer to the questions the universe is asking may already exist, written in papers that get 3 citations per year. The people who wrote those papers may be teaching at institutions that don't appear in the rankings, and the machinery built to find truth is, right now, actively excluding them. A blanket is always too short. This is how cosmologists describe the current state of model repair, and the image is accurate. Every proposed solution to the Hubble tension creates a new problem somewhere else. Every patch that fixes one anomaly stretches the fabric in a way that tears it at another seam. Early dark energy is the most developed proposal for resolving the Hubble tension. The idea: a brief episode of energy density in the early universe before recombination that slightly accelerated expansion during a critical window and changed the acoustic scale of the cosmic microwave background fluctuations. This shifts the Planck-derived Hubble constant upward, closer to the distance ladder value. The Hubble tension shrinks. The cost: early dark energy increases the amount of structure that should form in the universe. The S8 tension, which already shows the universe is too smooth, gets worse. You have now traded one anomaly for a larger version of another. Modified gravity approaches can address the S8 tension. Gravity, slightly weaker than general relativity on cosmic scales, would allow structure to grow more slowly, producing a smoother universe consistent with what surveys observe. The cost: a universe with modified gravity expands differently, and the expansion history no longer matches the Planck constraints in the way that standard the lambda cold dark matter model does. You have fixed S8 and damaged the Hubble tension fit. A completely new model of dark matter, with interactions or decay channels beyond the simple cold particle assumed in the lambda cold dark matter model, can address parts of the structure problem. The cost: the new dark matter model must simultaneously be consistent with everything the lambda cold dark matter model gets right, and the constraints on dark matter properties from multiple independent lines of evidence are now so tight that the available parameter space for modifications is extremely small. This is not a situation where the model needs a patch. This is a situation where the model itself may be structurally incompatible with the universe it is supposed to describe. A theory that cannot be fixed from within any of its components simultaneously is not a theory with gaps. It is a theory that has reached the boundary of its domain of validity, the same boundary that Newtonian mechanics reached when velocities approached the speed of light, the same boundary that classical physics reached when it tried to describe the interior of atoms. At that boundary, the theory does not need repair, it needs replacement, and the replacement, historically, does not come from inside the old framework. Let's build the full weight of this now. The technology you are using at this exact moment, every component of it, rests on physics that has been quantitatively confirmed to extraordinary precision. Your phone processes information using semiconductor junctions engineered with quantum mechanical band theory. Global positioning satellites run time corrections derived from special and general relativity to maintain the accuracy that lets the device in your pocket locate you to within a few meters. The internet runs on fiber optic cables that operate on principles derived from Maxwell's equations and quantum optics. Nuclear power plants and nuclear weapons work because the Standard Model correctly predicts the behavior of quarks and gluons in the nuclei of atoms. All of this works. The technology works consistently, reliably, at scale, across decades. And underneath all of it, the framework that produced these technologies cannot account for 27% of the matter in the universe, 70% of the universe's total energy content, the expansion rate of the universe, the origin of the lithium-7 discrepancy, the alignment in the oldest light, the smoothness of the current cosmic structure, the age of the galaxies the James Webb Space Telescope found, or the nature of the objects the James Webb Space Telescope found that don't belong to any known category. The parallel is exact. The Ptolemaic model of the solar system, with Earth at the center and planets moving on epicycles, made predictions accurate enough to navigate ships and calculate calendars for 1400 years. Ptolemaic astronomy worked. The tables it generated for the positions of planets were used by every navigator in the medieval Mediterranean. The model was wrong about the fundamental structure of the solar system in a way that couldn't be fixed by adding more epicycles. At some point, the number of epicycles required to maintain accuracy became its own argument against the model. The universe was not organized the way the model said it was, and the increasing complexity of the model was the first sign. Right now, the standard cosmological model has lambda for dark energy, cold dark matter, baryonic feedback prescriptions that require tuning, inflation parameters that remain unconstrained, and a growing list of post-hoc adjustments each time a new anomaly appears. The Hubble tension requires new physics before recombination or after. The S8 tension requires different new physics or modified gravity. The James Webb Space Telescope anomalies require revised star formation efficiencies or cosmological model revision. The lithium problem has been nudged but not solved. The axis of evil has no explanation. Each of these is an epicycle. The question that haunts everyone who has worked through this list carefully is the same question that confronted astronomers in the 16th century. At what point does adding another epicycle become evidence that the center is in the wrong place? The instruments just became good enough. That sentence contains a specific type of horror that takes a moment to fully assemble. It is not the horror of ignorance. It is the horror of precision. For most of human history, the universe was obscure enough that a wrong theory could fit comfortably inside the gaps. The instruments were crude, the measurements were imprecise. The anomalies were swamped by uncertainty. The model worked, or appeared to work, because the ruler wasn't fine enough to measure where it failed. Then came Planck. Then came the Wilkinson microwave anisotropy probe before it. Then came the Sloan Digital Sky Survey mapping hundreds of millions of galaxies. Then came the Dark Energy Survey and the Hyper Suprime Cam Subaru Strategic Program, and the Kilo Degree Survey measuring gravitational lensing to constrain the distribution of matter across cosmic scales. Then came the LZ detector running for 280 days with sensitivity 5 times greater than any previous weakly interacting massive particle search. Then came the Dark Energy Spectroscopic Instrument, mapping 14 million galaxies in its first 2 years of operation. Then came the James Webb Space Telescope, looking at the universe at ages no instrument had reached before. These instruments were built to confirm and refine. They were built by scientists who expected the standard model to pass the tests, who designed surveys to measure the parameters of the lambda cold dark matter model with increasing precision, who anticipated that higher precision would produce better constrained values of the same quantities. Instead, higher precision produced cracks. The Hubble tension is a crack that appeared when 2 precise measurements were compared. The S8 tension is a crack that appeared when large-scale structure surveys were compared to Planck. The dark matter non-detection is a crack that appeared when the detectors became sensitive enough to exclude the most plausible candidates. The James Webb Space Telescope anomalies are cracks that appeared when we could see far enough back in time. The generation of physicists who built these instruments is still alive. The anomalies they are finding are not converging toward resolution. They are diverging. Each new dataset brings tighter constraints and a worse fit to the standard model. The universe is not meeting us halfway. It is not simplifying as we look more carefully. Every window we open onto greater precision shows us a universe that fits the box less well than the less precise version did. We are in the moment, right now, today, in the year 2026, when the instruments became precise enough to prove something is wrong, and we have not yet built the instruments, or the theory, or the conceptual framework to show us what is right. Carlo Rovelli has written that the great revolutions in physics have not come from finding a missing piece in the existing picture. They have come from questioning a foundational assumption so deeply embedded that it was invisible. Newtonian mechanics assumed absolute time, a single universal clock ticking at the same rate everywhere. Special relativity dissolved that assumption entirely. Classical physics assumed that measuring a system doesn't change it. Quantum mechanics dissolved that assumption. The current crisis has the texture of a foundational assumption waiting to be dissolved. The cosmological principle, the nature of dark matter as a particle, the constancy of dark energy, the interpretation of quantum mechanics. One of these, or something more fundamental than any of them, may be the invisible assumption that a future physics will look back on the way we look back on the luminiferous ether. We do not know which assumption. We do not know who will question it. We do not know if the person who will see through it is currently a graduate student being told to focus on standard models, or a theorist whose papers are accumulating in a journal nobody reads. We know only this. The universe has been leaving us messages in 5 sigma signals and impossible timelines, and ghost particles and ancient light that remembers where we are. The messages are getting louder as our instruments improve. We can hear them now. We have been hearing them for years. The next step, the one that will look obvious in retrospect, the one that will reorder everything the way plate tectonics reordered geology and quantum mechanics reordered chemistry, that step has not yet been taken. The anomalies are not going away. They are multiplying. And somewhere in the data we already have, or in an experiment already running, or in a paper already written and not yet read by the right person, the universe may have already told us the answer. The question that should sit with you after everything we have been through today is not whether the standard model will eventually be replaced. It will. The question is what you believe right now, with the same certainty Lord Kelvin had in 1800, that the next generation of instruments will prove was a confidence you were never entitled to. What is your cosmological constant? What is the assumption so obvious to you that you have never thought to question it? Because the universe, as we now know with extraordinary precision, does not share your certainty. It has its own answer, and it has been waiting with infinite patience for us to become precise enough to hear it.